Hey everyone, welcome back to Chem Story. Ever wondered how two molecules with the exact same atoms can behave completely differently? They might have different boiling points, solubility, or even reactivity, and that's where isomers come in. Understanding isomerism is key to predicting how molecules behave, whether it's in chemical reactions, biological systems, or industrial processes. Alright, let's get started. Molecular formulas tell us what kinds of atoms are in a molecule and how many there are, but they don't show how those atoms are connected or arranged. That's why you can have molecules with the same formula, but completely different structures. And because of that, they end up having unique physical and chemical properties. We call these molecules isomers. Isomers can be grouped into two main categories: constitutional isomers and stereoisomers. Constitutional isomers, which we also call structural isomers, have the same molecular formula but different connectivity, meaning the atoms are bonded in different ways. On the other hand, stereoisomers have the same connectivity but differ in how their atoms are arranged in three-dimensional space. We can break down stereoisomers into two types: enantiomers and diastereomers. Enantiomers are like mirror images of each other, while diastereomers aren't. Diastereomers include cis-trans isomers and molecules that have multiple chiral centers. Alright, let's go through these one by one. First, let's take a closer look at constitutional isomers and how their connectivity impacts molecular properties. Constitutional isomers have the same molecular formula, but their atoms are connected differently, and that difference in connectivity means they end up with different IUPAC names. This difference in connectivity can also cause big changes in physical and chemical properties. For example, constitutional isomers can have different boiling points, melting points, solubility, and polarity. And because of these differences, they can be separated using physical methods. Some of them might have the same functional groups, while others have entirely different ones, which affects how they react. A classic example is N-butane and isobutane. Both of them have the same molecular formula, C4H10, but their structures are different. N-butane has a straight chain structure, while isobutane has a branch structure. This difference affects their boiling points and stability. Another great example is 1-butanol and diethyl ether. They both share the same molecular formula, but their functional groups are different. 1-butanol has a hydroxyl group, making it an alcohol, while diethyl ether has an oxygen bridge, making it an ether. Because of this, their boiling points, solubility, and reactivity differ. Constitutional isomers can also behave differently in chemical reactions. A good example is N-butyl bromide versus T-butyl bromide. These compounds don't react the same way in substitution and elimination reactions because of differences in steric hindrance and carbocation stability. Even though they have the same molecular formula, their structural differences lead to unique physical and chemical behaviors. On the other hand, stereoisomers have the same connectivity, but their atoms are arranged differently in space. Since the bonding sequence stays the same and only the orientation changes, their IUPAC names are usually identical, except for prefixes that indicate how the substituents are arranged. One classic example is cis-2-butene and trans-2-butene. In cis-2-butene, the two methyl groups are on the same side of the double bond, while in trans-2-butene, they're on opposite sides. This small difference in spatial arrangement has a big impact on boiling points and polarity. Another good example is 2,3-dibromopentane, which can exist as multiple stereoisomers. The prefixes 2R, 3R, 2R, 3S, 2S, 3R, and 2S, 3S tell us exactly how the atoms are arranged around the two chiral centers. Even though these molecules have the same connectivity, their spatial arrangement leads to different interactions and reactivity. One of the most important types of stereoisomers is enantiomers, mirror image isomers that you can't superimpose. They have the same physical properties and usually react the same way in most chemical reactions. But things change a lot when they're in a biological or chiral environment, especially when they interact with chiral reagents. A lot of pharmaceuticals are made up of enantiomers. In some cases, one form can be biologically active, while the other might be inactive or even harmful. That's why it's so important to distinguish between enantiomers when designing and synthesizing drugs. Another type of stereoisomer is diastereomers, and unlike enantiomers, they're not mirror images of each other. One common example is geometric isomers, like cis-2-butene and trans-2-butene. And here's another key point. Diastereomers can also include molecules with multiple chiral centers. A good example is threonine, an amino acid that has 2 chiral carbons and can exist in different stereoisomeric forms. Finally, let's talk about conformational isomers, or just conformers. What makes them unique is that they don't need to break any bonds to switch between forms. They just change shape by rotating around single bonds. In practice, we usually consider conformers as the same compound rather than distinct isomers under normal conditions. That's because they interconvert really quickly at room temperature. We only treat them as separate species when something like steric hindrance or low temperatures slows down their movement. A good example of a conformer is isane. It can exist in staggered and eclipsed forms. If we look at it using Newman projections, we can see how the hydrogen atoms move as the molecule rotates around its central carbon-carbon bond. Another well-known example is cyclohexane. It can adopt several different conformations like chair, half chair, twist boat, and boat forms. Out of these, the chair form is the most stable because it minimizes steric and torsional strain. To classify isomers in a systematic way, we can use a simple flowchart. First, check if 2 molecules have the same molecular formula. If they don't, they're not isomers. But if they do, that means they're isomers. All right, let's move on to the next step. The next step is to check their connectivity. If the connectivity is different, they're constitutional isomers, but if it's the same, they're stereoisomers. Next, see if the molecules are mirror images of each other. If they are, they're enantiomers. If not, they're diastereomers, which can include cis-trans isomers or molecules with multiple chiral centers. Understanding isomers is a fundamental part of organic chemistry. It helps us explain why molecules with similar formulas can behave so differently. Even small structural changes can have a big impact on reactivity, physical properties, and biological activity. All right, that's it for today. See you next time.